Ever wondered how your favorite snacks are made? In this behind-the-scenes look, we explore the high-tech factories and intricate processes behind Krispy Kreme donuts, M&Ms, and Pringles. From mixing and molding to frying and packaging, discover the precision and innovation that transform simple ingredients into the iconic treats we know and love. It all begins, unsurprisingly, with flour. Krispy Kreme uses a proprietary blend of enriched wheat flour, one formulated specifically for its lightness, protein balance, and ability to yield that signature fluffy bite. The flour is sourced from select mills that maintain tight quality control standards, ensuring the particle size, protein content, and gluten strength all fall within strict tolerances. Once delivered to the facility, the flour is stored in stainless steel silos under controlled temperature and humidity, preventing clumping and spoilage. Next, there's yeast, the biological engine behind the dough's rise. Krispy Kreme uses a commercial strain of baker's yeast known for its rapid activation, consistent fermentation profile, and neutral flavor. The yeast is usually delivered in refrigerated blocks or vacuum-sealed pouches to ensure maximum viability. Alongside the yeast, the other raw ingredients include non-fat dry milk powder, high-stability vegetable shortening, dextrose, salt, and water. Each of these ingredients plays a crucial role in shaping the final taste and texture of the donut. The shortening provides mouthfeel and moisture retention, while the dry milk lends a creamy undertone and enhances browning during frying. In the mixing phase, the ingredients are loaded into a spiral or planetary industrial mixer. The water is typically warmed to around 95 to 105 degrees Celsius before being introduced to activate the yeast. The mixer operates on a timed cycle, first gently combining the dry and wet components, then increasing speed to develop gluten and build dough structure. The dough is mixed until it achieves a smooth, elastic consistency with careful monitoring of temperature and hydration levels. If the dough becomes too warm, it risks overproofing, too cold, and fermentation is delayed. Sensors in the mixing bowl monitor the dough's internal temperature, moisture content, and even CO2 output to ensure consistency. Once the dough is formed, it enters the bulk fermentation phase. Giant stainless steel troughs, called dough rests, hold the dough as it ferments for the first time. During this period, the yeast metabolizes sugars and starches, producing carbon dioxide and ethanol. This expands the dough and begins developing its light, spongy structure. Krispy Kreme controls this step precisely, maintaining a temperature of around 80 degrees and 85% relative humidity in the proofing room. The dough rests here for approximately 30 to 40 minutes, depending on the batch size and ambient conditions. After bulk fermentation, the dough is transferred to a sheeting system. This is where things start to get visually impressive. The dough is rolled and flattened by calibrated rollers until it reaches a uniform thickness, typically between 10 to 12 millimeters. From here, it enters the cutting stage. A rotary die cutter stamps out perfect donut rings and holes in a continuous, automated process. The cutting dies are precision machined from stainless steel to ensure sharp, clean cuts and minimal dough waste. Any scrap dough is immediately collected by conveyors and reintroduced into the mixing system for reuse. Each donut ring now travels along a conveyor to the second proofing chamber, essentially a gigantic, climate-controlled cabinet lined with slow-moving racks. Inside, the donuts undergo their final proof, where they double in size due to continued yeast activity. The environment here is tightly regulated, around 90 degrees here and nearly 85% humidity. This proofing process typically lasts 30 minutes, but sensors embedded in the chamber walls adjust for ambient shifts in temperature or humidity, ensuring each donut achieves the perfect rise. Now comes one of the most mesmerizing parts of the process, the fry line. The fully proofed donuts are gently deposited into a continuous flow fryer using an overhead lifting mechanism that preserves their delicate structure. The frying oil, usually a high-stability palm or soybean blend, is maintained at a precise temperature of approximately 365 degrees. Each donut floats along the surface, first frying one side, then automatically flipping at the midpoint using a mechanical turner. This results in the even golden brown exterior Krispy Kreme is known for, with a pale, proof line around the center indicating proper fermentation. The frying process takes just under a minute per side, and the timing is crucial. Over-frying results in a dense, oily product. Under-frying leaves it doughy and structurally unsound. Oil filtration systems continuously clean and circulate the frying oil, removing carbonized particles and extending the oil's life while maintaining food safety. Once the donuts exit the fryer, they move onto a draining conveyor where excess oil drips away. The donuts are now fully cooked, but they're still bare, until they pass through the glaze waterfall. This is the stage most visitors at Krispy Kreme stores eagerly watch through the viewing window. The glaze itself is a proprietary blend of confectioner's sugar, water, and stabilizers, mixed in large heated vats to maintain fluidity. It's heated to a precise temperature to ensure it flows evenly over the donuts without soaking them. As the donuts travel beneath the waterfall, a curtain of glaze coats their entire surface in one smooth motion. The donuts continue to move along the belt for several feet to allow the glaze to set. During this time, cooling fans blow across the surface to speed up the crystallization process, giving the glaze its characteristic sheen and snap. At this stage, the original glazed donuts are complete, but not all donuts stop here. Many are diverted down alternate lines for filling, topping, or decoration. Filled varieties like custard, jelly, or cream-filled donuts are processed using pneumatic injection stations. The donuts are gripped and punctured automatically, and then a precise quantity of filling is injected into each center using calibrated nozzles. Topping lines include various enrobing stations for chocolate dips, icing drizzles, and even cookie crumb coatings, depending on the product line. Once decorated, the donuts pass through a final quality control checkpoint. Here, high-speed cameras, sensors, and human inspectors work in tandem to identify deformities, glaze coverage issues, or structural flaws. Any donut that doesn't meet the company's stringent standards is diverted and discarded or sent for animal feed, depending on local regulations. Now comes the packaging process. Original glazed donuts are usually arranged by robotic arms into branded trays or boxes, depending on the sales channel, whether destined for in-store display, grocery retail, or food service distribution. Boxes are barcoded, date-stamped, and sealed automatically. For freshness, Krispy Kreme relies on just-in-time manufacturing. Many facilities bake and ship multiple times per day, with some outlets even co-located within the production plant itself to reduce handling and delay. For external distribution, the boxed donuts are loaded into climate-controlled trucks equipped with racking systems that prevent damage during transit. These trucks make scheduled routes to retail locations, grocery partners, and kiosk outlets, often arriving just hours after the donuts were made. Once on site, employees stock the shelves or display racks, ensuring the donuts are sold within their optimal freshness window, typically less than 24 hours. Meanwhile, any donuts not sold by the end of the day are generally removed to preserve Krispy Kreme's reputation for freshness. In some regions, unsold inventory is donated to food banks or repurposed, while others adhere to strict disposal policies. Throughout this entire process, automation and precision engineering play a central role. From programmable logic controllers managing the mixing and proofing cycles, to machine vision systems inspecting glaze coverage, every step is optimized for consistency, safety, and speed. The machinery involved is custom designed, often proprietary, and requires teams of trained technicians to maintain. Clean-in-place systems are installed throughout the facility to sanitize pipes, mixers, glaze troughs, and conveyors between production runs. This minimizes downtime while ensuring compliance with food safety regulations. Every aspect, from microbial swab testing to allergen control and traceability, is monitored via centralized software platforms, which can track each batch of donuts from flour silo to store shelf. The story of every M&M starts with one essential component: chocolate. The heart of a standard M&M is a solid drop of milk chocolate, though other varieties, like peanut, almond, crispy, pretzel, or peanut butter, feature different cores. But regardless of the variety, the production begins in the chocolate refining department, where raw ingredients such as cocoa liquor, cocoa butter, sugar, and milk solids are blended to make a smooth, consistent chocolate base. The chocolate used in M&Ms is tailored for firmness and melt resistance, specifically engineered to maintain its structure during the coating process. Large stainless steel tanks are used to melt and hold the chocolate at controlled temperatures. Automated valves and mixers regulate temperature, viscosity, and flow characteristics. Chocolate destined for M&M production must be carefully refined to reduce particle size, usually to around 20 microns. This is done in multiple stages using equipment like ball mills, roller refiners, and conchas. These machines apply friction, pressure, and shear force to break down the solid particles until the chocolate achieves its desired mouthfeel. Once refined, the chocolate is pumped to depositors, automated nozzles that precisely dispense the liquid chocolate into molds or droplet-forming equipment. For the classic M&Ms, the chocolate is dropped onto a cool, rotating belt in small, round portions, forming button-shaped discs. These droplets are cooled rapidly using chilled air tunnels to harden them before further processing. The cooled chocolate centers are then collected and sent to the coating drums. These are large, rotating pans, sometimes referred to as dragees pans or coating kettles, where the hard candy shell is gradually built around the chocolate core. This is the heart of the M&M production process and one of the most visually striking steps in the factory. The coating process is a slow and incremental buildup, achieved by spraying a fine mist of sugar syrup onto the tumbling chocolate centers, then drying and hardening that layer before repeating the cycle. Each coating drum can hold hundreds of thousands of chocolate centers at once. As the drum rotates, a fine spray of syrup, consisting mainly of sugar and water with optional corn syrup, is applied in short bursts. Warm air is then blown into the drum to dry the layer, allowing the sugar to crystallize into a thin, hard shell. This cycle is repeated dozens of times, each time adding a microscopically thin layer to build up the final shell thickness. Over time, this layering transforms the centers from soft chocolate buttons to perfectly round, hard-shelled candies. During this stage, technicians monitor coating uniformity, size consistency, and drying times using high-speed cameras and inline sensors. If the temperature or humidity in the coating room deviates too far from spec, it can ruin an entire batch, leading to shell cracking or poor adhesion. Once the desired shell thickness is achieved, the M&Ms are polished to give them their signature shine. This is done by adding polishing agents, such as carnauba wax or beeswax, to the coating drum in very small amounts. These natural food-grade waxes help create a glossy finish that not only enhances visual appeal, but also helps prevent sticking and moisture absorption during storage. The polishing phase takes less time than coating, but must be precisely timed to avoid overwaxing, which can result in a greasy or smeared appearance. The next step is color application, which may seem simple, but is, in fact, a carefully controlled phase. M&Ms come in a variety of colors, typically red, orange, yellow, green, blue, and brown. The color coding is applied using a sugar-based dye solution, sprayed in another round of layering inside rotating pans. Each batch is divided according to how many of each color are required. Food-grade colorants are mixed with water and a binding agent to ensure even adherence to the existing shell. After the colorant is applied, warm air is used to dry the layer, and another wax polish may be added to lock in the color and maintain shine. The factory uses precise batch tracking and automated scheduling software to ensure the correct number of each color is produced. For example, if red accounts for 20% of a standard bag's color distribution, the system ensures exactly that percentage is created during the run. This attention to detail keeps the consumer experience consistent across bags, boxes, and geographic regions. After color coding, the candies proceed to the printing station, where the iconic M is stamped on each piece. This is accomplished using high-speed, food-safe ink printers. The M&Ms are gently vibrated into a single layer on a moving conveyor belt that aligns them properly for stamping. The white edible ink is applied using a flexographic or offset stamping mechanism that imprints the M logo without damaging the candy's surface. To ensure accuracy, machine vision systems monitor the printing in real time, checking for clarity, alignment, and completeness. Any candies that are misprinted or blank may be removed by pneumatic air jets and diverted for recycling or reprocessing. Now the M&Ms are ready for packaging. This phase of production involves a combination of robotics, weight-checking systems, and packaging machinery that operates at astonishing speeds. The candies are directed into vertical form-fill-seal machines or horizontal flow wrappers, depending on the packaging format. Multi-head weighers dispense precise quantities of M&Ms into each bag or pouch, ensuring weight compliance to legal standards. The packaging film is heat-sealed to form a tamper-evident, airtight barrier that preserves freshness and extends shelf life. For bulk formats, such as large tubs, party-sized bags, or vending packs, the process is slightly different but still highly automated. The machines are programmed to handle various product sizes, materials, and pack types without compromising accuracy. Barcodes, expiration dates, and lot numbers are printed onto each package to allow for traceability. Once packaged, the products are conveyed to case packing robots, which group them into cartons or boxes for shipping. These cases are then sealed, palletized by robotic arms, and shrink-wrapped for transport. Pallets are stored temporarily in climate-controlled warehouses before being loaded onto distribution trucks that carry them to retail centers, convenience stores, vending machine suppliers, and international shipping hubs. Throughout the entire process, food safety and quality control are paramount. The factory floor is governed by strict hygiene protocols. Employees are required to wear sanitary gear, and the equipment is sanitized regularly using automated clean-in-place systems. Random sampling is conducted at every critical control point, from chocolate refining to shell thickness to final packaging. Laboratory testing checks for microbial contamination, allergen presence, and chemical composition. Quality assurance teams also perform taste tests, structural integrity tests, and heat resistance trials to ensure the product meets Mars Inc.'s global standards. In the case of peanut or almond M&Ms, the process is similar but begins with nut preparation. Peanuts, for instance, are roasted in-house to develop their flavor and reduce microbial load. They are then cooled, sorted by size, and coated in a preliminary layer of chocolate before undergoing the same sugar shell layering process. Their irregular shape requires adjustments to coating speed and rotation patterns to ensure even coverage. The engineering behind M&M production is not only a marvel of food science, but also a study in high-speed manufacturing. Thousands of M&Ms can be produced every minute, yet each one must look and taste exactly the same. This requires the coordination of multiple disciplines: mechanical engineering, chemistry, automation, logistics, and sensory evaluation. The process begins not with whole potatoes, but with dehydrated potato flakes and potato starch. These form the base of the Pringles dough. The flakes are manufactured off-site through a separate drying process where peeled, cooked potatoes are mashed and then passed through drum dryers to remove water, creating thin, crisp sheets of dried potato. These are ground into fine granules and delivered to Pringles production facilities in bulk quantities, stored in climate-controlled silos to maintain moisture levels and prevent clumping. To this potato base, manufacturers add a precise blend of rice flour, corn flour, and wheat starch. This multi-starch formula gives Pringles their distinctive light, yet durable crunch, firmer than a classic chip, but less dense than a cracker. Each ingredient is selected for its functional properties. Rice flour contributes to lightness and reduces oil absorption. Corn flour provides structure and contributes to the crisp texture. Wheat starch acts as a binding agent and helps form the dough into a cohesive sheet. Inside the factory, these dry ingredients are metered into high-capacity industrial mixers. Water is added gradually, and the mixture is agitated until a cohesive dough forms. The consistency of the dough is critical. It must be pliable enough to be rolled and shaped, yet stiff enough to hold its form during frying. Too much water would cause the crisps to bubble and deform. Too little, and they would crack or crumble during processing. After mixing, the dough is conveyed onto a series of steel rollers in a sheeting machine. These rollers press the dough into a continuous, thin sheet, typically about 0.7 to 1 millimeter thick. The uniformity of this sheet is crucial, as even slight thickness variations can affect how the chips fry, blister, and brown. Advanced sensors mounted near the rollers continuously monitor sheet thickness, feeding data to the control system, which makes micro adjustments in real time. Next, the sheeted dough passes under a rotary die cutter. This is a cylindrical cutter with thousands of identically shaped molds engraved into its surface. As the sheet moves beneath it, the die cuts out dozens of curved oval crisps at a time, each one precisely measured to match Pringles' iconic dimensions, around 6.5 centimeters long and 5.5 centimeters wide, shaped with a unique double-curved profile known as a hyperbolic paraboloid. This mathematical shape isn't just aesthetic, it offers stackability, strength, and an audible crunch due to its uniform stress distribution. The dough scrap that remains between the cutouts is immediately separated and returned to the beginning of the process. Conveyor belts collect and transport the unused dough back to the mixer, where it is reincorporated into fresh dough. This closed-loop system minimizes waste and ensures efficiency in ingredient usage. Once cut, the raw crisps are gently lifted from the sheet using suction cups or air jets and placed onto a moving metal belt composed of dozens of concave molds. Each mold perfectly matches the chip's final saddle shape. This belt then moves the raw crisps into the fryer, an enormous stainless steel bath filled with hot vegetable oil, maintained at a consistent temperature of around 170 to 180 degrees. The crisps are submerged for approximately 11 seconds, long enough to remove moisture and induce a Maillard reaction, giving them their light golden brown hue and toasty flavor. Unlike traditional deep-fried potato slices that can curl, bend, or form bubbles, the Pringles molds maintain each crisp's structure during frying. Because the crisps are uniformly thin and precisely shaped, they fry evenly with no dark spots or oil saturation. Excess oil is quickly removed as the crisps exit the fryer and pass over a series of vibrating conveyors and air knives, high-pressure jets that blow away any surface oil or crumbs. At this point, the freshly fried crisps are hot, dry, and unseasoned. They move into the seasoning tunnel, a long, rotating drum equipped with sprinklers or spray nozzles. Here, flavor powders, ranging from classic original to sour cream and onion, cheddar cheese, or barbecue, are evenly applied as the crisps tumble and rotate. The flavor powders are formulated to stick to the crisp's surface via residual oil left from frying. In some varieties, additional ingredients such as powdered cheese or dehydrated vegetables are included in the seasoning blends. To prevent flavor loss and preserve freshness, the seasoned crisps are quickly cooled using forced air systems before entering the packaging phase. This cooling is critical. If the crisps are too warm, condensation can form inside the package, leading to soggy chips and microbial risk. Once cooled, they are conveyed to the stacking and canning line. This is where another defining feature of Pringles becomes prominent: their tubular canister. The stacking machine uses a system of synchronized mechanical arms, optical sensors, and robotic paddles to stack crisps one by one into perfectly aligned columns. This process is remarkably fast and precise. A sensor verifies each crisp's shape and orientation before it's inserted into the growing stack. Once a full stack reaches the correct height, typically around 80 to 100 crisps, depending on the packaging size, it is inserted vertically into a cardboard can that's been pre-formed and lined with a metallized film to prevent oil seepage and moisture intrusion. Each can is equipped with a plastic bottom, which is ultrasonically welded or heat sealed in place before filling. After the crisps are inserted, a foil lid is applied and hermetically sealed using induction heat or pressure bonding to ensure an airtight closure. A plastic snap-on cap is then placed on top, providing resealability for consumer convenience. The filled cans are then labeled and date-coded. Each can receives a printed batch number and expiration date to ensure traceability throughout the distribution chain. Vision inspection systems scan each can to ensure it is filled to the correct level, sealed properly, and free of any external defects like dents or mislabeling. Cans are grouped into multi-packs or cartons by robotic arms and placed on pallets for storage or shipment. Depending on demand and product line complexity, different varieties of Pringles may be produced in separate production runs on the same line, requiring quick and thorough cleanouts between batches to prevent flavor cross-contamination. From here, Pringles are shipped to distribution centers, retailers, and convenience stores across the globe. Thanks to the uniform shape and rigid packaging, they travel exceptionally well, with minimal breakage compared to traditional bagged chips. This durability, coupled with the brand's distinct identity, has made Pringles a staple in global snack markets. Sanitation and quality control are central throughout the process. Each stage of production, from dough mixing to final packaging, is monitored by automated control systems and human operators. Random samples are collected for lab analysis to check moisture levels, oil content, seasoning distribution, and texture. Microbial testing ensures no contamination occurs during handling. Metal detectors and X-ray machines inspect each can before shipping to catch any foreign objects that may have entered the line. Allergen controls are strictly enforced, particularly when switching between varieties like original and cheddar cheese. In addition to ensuring food safety, the factory design and equipment layout support continuous cleaning. Many machines feature clean-in-place systems that pump sanitizing fluids through the equipment without requiring disassembly. Air filtration systems and positive pressure rooms minimize the risk of dust and airborne contaminants affecting product quality. Beyond the manufacturing floor, the creation of new Pringles flavors and formats involves food scientists and R&D specialists who develop seasoning blends, test mouthfeel, and conduct sensory panels with trained tasters. Innovations like Pringles Wavy or Pringles Scorchin follow the same base process, with minor adjustments in dough formulation or seasoning protocols. Despite their high-tech origin, Pringles still deliver a simple satisfaction, a crisp, flavorful bite that feels familiar and fun. But behind that enjoyment is a complex dance of precision equipment, mathematical shaping, and carefully designed formulations. From powdered potatoes to perfectly stacked crisps, every Pringle is a product not just of flavor, but of industrial ingenuity. A testament to how food science can transform something as humble as a potato into a globally recognized snack. The production of Red Bull starts long before the filling lines come to life. It begins at the sourcing and logistics stage, where each raw material used in the drink is carefully specified, contracted, and verified to meet the company's global quality standards. Although the ingredient list appears relatively simple, water, sucrose, glucose, citric acid, carbon dioxide, caffeine, taurine, B vitamins, and flavorings, the level of control and traceability involved in acquiring each component is remarkably complex. We begin with the most abundant ingredient: water. Water makes up the vast majority of the product, and its quality is absolutely critical. Unlike municipal tap water used in smaller food and beverage operations, the water used in Red Bull production must conform to pharmaceutical-grade purity standards. This means it undergoes extensive filtration, mineral balancing, and microbiological testing before it ever reaches the mixing tanks. In most Red Bull factories, water is drawn from deep, protected aquifers or dedicated water sources that are tested daily. The water is pumped into on-site treatment plants where it first passes through coarse filtration to remove particulate matter like sand or debris. It is then passed through activated carbon filters to strip away chlorine, organic compounds, or any remaining trace contaminants that could affect taste or chemical stability. The next step is typically reverse osmosis, a membrane-based filtration system that removes dissolved solids at a molecular level. This process reduces the water to an ultra-clean base, free of minerals, microbes, or off flavors. Once the water is purified, it enters holding tanks constructed from polished stainless steel. These tanks are fitted with level sensors, CIP spray heads, and temperature regulation systems to maintain stability. Water is kept in motion using gentle agitators or circulation pumps to avoid stagnation and ensure readiness for blending. Meanwhile, the sugar content of Red Bull, derived from both sucrose and glucose, requires its own specialized preparation. Red Bull uses a combination of these two carbohydrates to create its sweet but not overly cloying flavor profile. These sugars are sourced from sugar beets and corn and arrive at the plant either in dry crystalline form or as concentrated syrups, depending on regional supply chains. In facilities that receive dry sugar, the ingredient is pneumatically conveyed from delivery trucks into sealed sugar silos. These silos are climate controlled to prevent moisture absorption and equipped with weight sensors to track inventory in real time. When ready for production, the sugar is transferred to large dissolving tanks where it is combined with hot, purified water and mixed using high shear agitators to create a uniform syrup. This syrup is passed through mesh filters to remove any undissolved particles, then sent to a holding tank where it is cooled and held under sterile conditions. For glucose syrup, the process is slightly different. Delivered in bulk liquid containers or tanker trucks, the syrup is pumped through heated, insulated lines to prevent crystallization during transfer. Inline flow meters and viscosity sensors are used to ensure consistency. Once in the storage tanks, the glucose syrup is sampled and tested for pH, sugar concentration, and microbial stability before being cleared for blending. Now comes taurine, one of the most distinctive and chemically sensitive ingredients in the formula. Taurine is an amino acid-like compound that plays a role in neurological development and cellular hydration. It is synthesized in pharmaceutical-grade chemical plants through a controlled reaction involving ethylene oxide and sodium bisulfite, resulting in a high-purity crystalline powder. Red Bull does not extract taurine from animal sources. It is entirely synthetically produced for purity and consistency. Taurine is delivered to the beverage plant in sealed drums or lined bags inside rigid totes. Upon arrival, each container is inspected and sampled. The contents are tested for purity using high-performance liquid chromatography and screened for heavy metals and microbial contamination. Once cleared, the powder is either stored in a dry room or moved directly to the batching area, where it is weighed with precision down to the gram using automated ingredient scales. Caffeine, another central functional ingredient, is handled with similar precision. Synthetic caffeine, which is chemically identical to naturally occurring caffeine, is the preferred form in most facilities due to its purity and consistency. It arrives in fine white powder form, packaged in airtight containers to prevent oxidation and contamination. Like taurine, caffeine is dosed in tightly controlled quantities. Too much, and the drink becomes bitter or risks regulatory violation. Too little, and the expected stimulant effect may be lost. B group vitamins, specifically niacin, pantothenic acid, vitamin B6, and vitamin B12, are delivered in stabilized powder form. These micronutrients are highly sensitive to heat, light, and oxygen, so they are packaged in light-blocking, nitrogen-flushed containers. They are stored in temperature-controlled rooms and only opened at the time of production. Dosing is managed using micro-feeding systems, capable of adding quantities in the milligram range with high accuracy. Citric acid, used to balance sweetness and enhance shelf life, is one of the more straightforward ingredients. It arrives in either crystalline or liquid form, depending on plant setup. Like the sugars, citric acid is dissolved or diluted in purified water, filtered, and then pumped into blending tanks using stainless steel sanitary piping. It is included not only for flavor, but also to regulate the final pH of the drink, which has an impact on microbial resistance and carbonation behavior. The final core ingredient, prepared before blending, is carbon dioxide. Although it's added at the end of the line during filling, CO2 must be stored on-site in large insulated tanks under high pressure. This gas is certified food grade and must meet stringent standards for purity and dryness. Impurities in the gas, such as hydrocarbons or sulfur compounds, can result in off flavors or affect carbonation stability. Inline purifiers and moisture traps ensure that the gas remains within specification as it travels to the carbonation units. At this stage, all the major ingredients have been separately received, prepared, filtered, and stored in secure holding tanks, each one monitored by a network of sensors and controlled through a centralized process control system. The factory is now ready to enter the next phase, the blending and batch formulation process, where the base liquid is built step by step from these prepared components under tightly monitored conditions. Inside the blending hall of a Red Bull manufacturing plant, massive stainless steel tanks, often tens of thousands of liters in capacity, stand ready to receive pre-prepared ingredients. Each of these tanks is built with industrial mixers at the base and along the walls, with baffles designed to eliminate dead zones and ensure even distribution of all ingredients once mixing begins. These aren't just glorified vats, they're engineered systems with flow sensors, agitation controllers, and automated dosing inlets. Blending starts with the base, purified water. A calibrated volume is pumped into the blending tank. From here, the sweetener solution is added. By this point, the sugar and glucose have been dissolved into a consistent syrup in separate vessels and passed through fine mesh filters to remove any undissolved particles. They're now gravity-fed or pumped into the main tank through metered valves, which record the exact volume added in real time. At this stage, the solution is still colorless, with a mild sweetness and a viscosity slightly thicker than water. Stirring begins slowly, just enough to encourage circulation without aerating the mixture prematurely. Once the sweet base is established, the functional ingredients are added in a very specific sequence. This isn't just for convenience, it's chemical. Caffeine, taurine, and vitamins each behave differently depending on the pH, temperature, and concentration of the liquid they're introduced into. To ensure even dissolution, caffeine is dosed in carefully, often pre-blended into a neutral, aqueous solution to avoid clumping. Taurine, being more soluble, can be introduced directly, but at a steady rate to avoid localized saturation. The temperature of the blend is strictly controlled during this entire process, typically kept between 10 degrees C and 15 degrees. Keeping the temperature low helps prevent degradation of the heat-sensitive components, especially the B vitamins, and also limits the risk of microbial growth. Inline cooling jackets on the tank walls help regulate this, while digital sensors constantly send data to the factory's main control panel. After the active ingredients are in and fully dissolved, the next step is homogenization. While Red Bull is a clear drink and doesn't have oil-based elements like some emulsified beverages, this process is still used to ensure complete molecular distribution. A high-speed rotor-stator mixer is activated to subject the liquid to intense shear forces, ensuring that no microclumps or undissolved pockets remain. Think of this as the industrial version of making sure your recipe has no lumps, but at a scale where a few unblended grams could ruin an entire batch worth millions of servings. Once homogenized, the blend is passed through a fine filter system, often absolute rated filters that remove particles down to the sub-micron level. This is the final polish of the beverage, ensuring not just clarity and texture, but also eliminating any particulate matter that could interfere with carbonation or filling equipment. Now, the finished liquid base is sent to a storage tank, often referred to as the balance tank, which feeds the carbonation system. At this stage, the liquid is still uncarbonated. Carbonation must be done with surgical accuracy, both in timing and in gas levels. Too early, and carbon dioxide can escape during filling. Too late, and the drink will feel flat. Before carbonation, the balance tank contents are degassed using a gentle vacuum system to remove any dissolved air from the blend, air that could interfere with carbonation or introduce unwanted oxygen into the final product, leading to flavor instability over time. Carbonation is introduced through a high-precision saturator. This device uses temperature, pressure, and turbulence to force carbon dioxide into the liquid. The lower the temperature, the more CO2 the liquid can absorb, so the beverage is chilled further just before entering the saturator. Inside the unit, the liquid flows in a turbulent spiral while pressurized CO2 is injected. Sensors monitor saturation levels down to fractions of a gram per liter, and the flow is fine-tuned via automated valves. Once carbonated, the beverage is immediately transferred to the filler line. No storage, no delay. At this point, any agitation or exposure to heat could cause gas to escape, so the tubing, valves, and tanks are all designed to reduce turbulence. The product is now ready to be introduced into cans. Filling lines in a Red Bull factory are among the fastest and most technologically advanced in the beverage industry. The cans themselves arrive at the plant in stacks of blank aluminum cylinders, unprinted or pre-printed depending on the factory setup. These cans are depalletized automatically and conveyed upright to the rinser station. Here, they're inverted and sprayed internally with deionized water or sterile air to remove dust or particulates. From the rinser, the cans travel on a conveyor to the filler. This machine uses a gravity or counter-pressure system to fill each can precisely while preserving carbonation. The can enters the fill station, is sealed around the top rim with a flexible gasket, and then filled from the bottom up with cold, pressurized beverage. Fill levels are controlled within a margin of plus 0.5 grams to ensure legal compliance with net content regulations and consistent customer experience. Immediately after filling, the can passes to the seamer, where a pre-formed aluminum lid, known as the end, is dropped onto the top and crimped into place. This creates an airtight seal. Seamers are some of the most mechanically intricate machines in the entire facility, operating at speeds of over 1,000 cans per minute while performing multiple precision operations in less than a second per unit. After sealing, the cans are rinsed externally to remove any spillage and pass through a drying tunnel. They then enter the inspection phase. Here, cameras and sensors verify the seal integrity, check fill levels using X-ray or gamma ray detection, and inspect for dents, deformations, or labeling defects. Any can that fails inspection is automatically ejected from the line. Cans that pass all tests are conveyed to the packaging station. Depending on the market, cans are grouped in 4-packs, 6-packs, or full case trays. Robotic arms or mechanical pushers group the cans and slide them into shrink-wrap tunnels or cardboard sleeves. Once bundled, packs are palletized, either by layer robots or high-speed stackers, wrapped with stretch film and labeled with product codes, production date, and batch information. These pallets are now staged in a temperature-controlled warehouse, ready for distribution. The real-time tracking of every single ingredient, batch, fill date, and can code allows for full traceability from ingredient origin to final shipment. In the next section, we'll follow how those pallets move through the global distribution network and how Red Bull's quality assurance, shelf stability testing, and cold chain monitoring ensure that each can performs exactly as intended from Austria to Australia. With the Red Bull cans now filled, sealed, and packed onto pallets, the production process transitions into the next highly critical phase: post-production handling, distribution management, and long-term quality assurance. Although the drink is technically finished, the factory still bears significant responsibility for maintaining its integrity through storage, shipping, and shelf life. This phase involves coordinated warehouse systems, climate control, global logistics networks, and extensive quality monitoring procedures that extend well beyond the factory floor. All of it is designed to ensure that every can of Red Bull tastes and performs identically, whether it's consumed in Bangkok, Berlin, or Boston. Once the pallets are complete, they are conveyed from the packaging area into the outbound staging zone, a dedicated part of the facility built to manage finished goods. This area is laid out with barcode scanners, RFID readers, and automated warehouse software. Each pallet is scanned as it enters, recording not only the product type and production date, but also its batch code, can format, and destination market. This digital tracking ensures complete traceability of every pack produced. The system also flags any inventory that is out of rotation or that has not been cleared by the final quality audit. Pallets are stored in high bay racking systems that can reach 5 or 6 levels high. These racks are arranged to maximize airflow and minimize temperature variation, as environmental stability is critical for energy drinks. The warehouse is kept within a strict range of temperature, typically between 18 degrees Celsius and 22 degrees Celsius, and humidity under 60% to preserve carbonation, prevent packaging degradation, and protect flavor stability. Light exposure is minimized using tinted overhead fixtures or motion sensor lighting, since prolonged light can interact with the contents of clear or thin-walled aluminum containers, subtly affecting taste or causing internal discoloration. But before any pallet leaves the facility, it must be cleared through a final release protocol. This involves sampling from each production batch, typically 1 out of every few thousand units. These samples are sent to the in-house quality control laboratory for a battery of tests. Microbial testing is conducted to ensure that the beverage remains free from bacteria or yeast. Although Red Bull is not pasteurized, its low pH and high CO2 content provide natural protection, and the factory's sterile filling conditions act as a critical control point. Nonetheless, post-fill samples are incubated in climate-controlled chambers for 72 hours and checked for any microbial activity. Simultaneously, chemical stability tests are performed to verify that the concentrations of caffeine, taurine, sugars, acids, and vitamins are within tight tolerances. Each test is logged, reviewed, and signed off by senior lab technicians. Once the data passes review, the production batch is cleared for shipping. At this point, the factory releases the inventory into the hands of the logistics team, which organizes regional and international transportation. The Red Bull supply chain is designed around speed, efficiency, and protection. Because the drink is sold in more than 170 countries, it requires a global distribution system that can manage environmental variables, transit times, and regulatory differences across continents. Each factory or co-packing facility is paired with multiple logistics hubs, either operated directly or through third-party logistics providers, each specializing in cold chain monitoring, customs clearance, or last-mile delivery. Shipping conditions are tightly controlled. While Red Bull cans are shelf-stable and do not require refrigeration, they are sensitive to excessive heat and should not be exposed to prolonged freezing. Therefore, all transportation routes are mapped to avoid extreme temperature exposure. Trucks are preconditioned before loading, ensuring that their interior holds the correct temperature before the first pallet is moved in. During loading, factory staff monitor not just product count and pallet orientation, but also airflow paths and stacking height to ensure that cans are not crushed or deformed during transit. Each truck or container is equipped with temperature loggers and shock sensors. These devices record environmental data every few minutes and store it until offload. If a truck breaks down, or if the cargo passes through an area of extreme temperature fluctuation, the logs will show it. When the shipment arrives at its distribution center or regional warehouse, receiving teams will review the data. If it falls outside the acceptable range, the load may be held, inspected, or even rejected. This provides a full audit trail from the moment the product left the factory to its arrival at the next checkpoint. For international shipments, the process becomes even more complex. Export shipments must comply with country-specific food regulations. In some cases, ingredients must be declared differently. In others, labeling requirements vary. The factory works with regulatory teams to produce market-specific versions of the product, sometimes varying the language, caffeine content, or vitamin mix to meet local laws. Each international pallet is assigned a customs manifest, a certificate of analysis from the lab, and a temperature log that confirms it stayed within the specified range throughout the journey. Once Red Bull arrives at its destination warehouse, whether it's in Tokyo, Johannesburg, or Chicago, it enters a new round of inventory rotation and quality checks. Local distribution centers store the product under similar environmental controls, and the product is rotated using FIFO systems to minimize aging. While the drink has a long shelf life, usually around 18 months, Red Bull's internal standards aim to deliver most of its inventory to retailers within just a few weeks of production to ensure maximum freshness. Some pallets will be broken down into smaller loads and sent to large supermarket chains. Others are routed to gas stations, bars, vending machine operators, or e-commerce fulfillment centers. In each case, local merchandisers and sales teams monitor product placement, stocking practices, and display temperatures. Although Red Bull does not require refrigeration, many retailers choose to chill it for immediate consumption, and Red Bull provides branded refrigeration units to support this. At the store level, Red Bull continues to run random quality checks, known as in-market assessments. These include taste tests, packaging inspections, and code date verifications. Data from these assessments is sent back to the factory quality system and reviewed quarterly. If trends are observed, like subtle flavor degradation in warmer climates or denting during local transit, factory protocols are updated and packaging specifications may be revised. This feedback loop is critical to maintaining the uniform experience that Red Bull is known for globally. Even after the product has been sold, the process doesn't stop. Red Bull maintains traceability for every batch through lot codes printed on the bottom of each can. If a customer reports an issue, the quality team can pull that code, identify the exact production line, shift, and even the technician who oversaw that batch. While issues are rare, this system allows the company to investigate and resolve problems with precision, minimizing waste and protecting brand integrity. Beyond logistics and troubleshooting, the factory also conducts long-term aging tests. Retained samples from every production batch are stored under controlled conditions for 12 to 24 months. These samples are periodically tested for flavor consistency, vitamin retention, carbonation, and packaging durability. This helps inform decisions about shelf life labeling, new packaging materials, and product reformulation. Back at the plant, everything learned during distribution feeds into continuous improvement efforts. Engineers analyze transit shock data to refine pallet structures. Chemists review long-term flavor curves to tweak the balance of acids and preservatives. Operators attend refresher training sessions on fill line calibration, cap torque standards, and seaming pressure. The plant becomes not just a factory, but an evolving ecosystem of precision, designed to produce millions of cans with microscopic tolerance and global dependability. Inside Red Bull's production and R&D infrastructure, innovation continues quietly and continuously alongside the high-speed filling lines. While the mainstream drink is tightly standardized, parallel systems exist within the factory environment for development, testing, and controlled rollout of new variants, flavors, and formats. These operations are often confined to specialized pilot plants, small-scale, highly modular manufacturing lines where experimental recipes and new packaging concepts are trialed without disrupting the core production flow. These pilot lines mimic every critical phase of full-scale production, from batching to carbonation and filling, but at reduced volumes. Engineers can simulate the thermal and mechanical stresses of the full-size process, adjusting flow rates, temperature profiles, and equipment speeds to understand how small tweaks to formula or process could affect outcomes. Whether testing a sugar-free variation, a new flavor blend, or a limited edition can size, the data collected here determines what does and does not graduate to full factory rollout. Each new formula undergoes rigorous stress testing. Finished samples are subjected to cycles of heat, cold, vibration, and light exposure to simulate real-world transport and storage conditions. Flavor retention is tracked over time through sensory analysis and gas chromatography. Carbonation levels are monitored for stability across packaging types and temperatures. Packaging engineers assess how different aluminum can wall thicknesses or end configurations perform under pressure, especially when new recipes require modified CO2 saturation. If a variant clears all physical and chemical tests, the next step is consumer trials. In select cases, Red Bull collaborates with regional markets to test launch a new flavor or packaging size in a limited territory. These micro launches help measure demand, gather feedback, and identify operational issues before scaling up. Even then, these limited variants are often produced on flexible equipment lines reserved specifically for such runs, using interchangeable molds, modular filler heads, and smaller tank systems. Even small changes, like switching from a matte to a gloss label finish, require recalibration of the vision systems on the inspection line. Barcode scanners must be trained to detect label variations, and automated reject mechanisms must be tested to avoid false positives. This ensures no disruption in quality control, even when the product range temporarily expands. Back in the lab, teams also study ingredient interactions under extreme use scenarios. Unlike many fast food chains that rely heavily on pre-cooked, frozen, or highly processed food products, Five Guys has built its entire business model on quality, freshness, and simplicity. That simplicity, however, hides a remarkably complex and carefully controlled supply chain that delivers consistent, high-quality ingredients to thousands of restaurants across the US and internationally. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated. Five Guys moves thousands of pounds of beef and buns through a supply chain so intense it runs like a high-speed burger machine. Behind every fresh, made-to-order meal is a massive factory system designed to deliver consistent flavor with zero shortcuts. In this documentary, we go inside the operation powering one of America's most iconic burger chains, from raw ingredients to grill-ready perfection. Unlike many fast food chains that rely heavily on pre-cooked, frozen, or highly processed food products, Five Guys has built its entire business model on quality, freshness, and simplicity. That simplicity, however, hides a remarkably complex and carefully controlled supply chain that delivers consistent, high-quality ingredients to thousands of restaurants across the US and internationally. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean-to-fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground, and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated, but the buns are loaded in temperature-controlled staging areas and packed in sealed corrugated boxes to maintain freshness during transit. Any deviation in delivery, timing, or packaging temperature triggers a rejection at the restaurant level. In-store, the buns are stored at room temperature in designated bread racks, often rotated using FIFO principles. Staff members are trained to inspect buns visually and by touch. Any signs of excess firmness, moisture, or spotting lead to immediate disposal. Each bun is hand-prepared on-site, toasted on a grill with a light coating of melted butter before it becomes the vehicle for the burger build. This final touch, though simple, is only possible because of the structural integrity and texture delivered by the bakery's industrial process. Now that the core components of a Five Guys burger are accounted for, the beef, the fries, and the buns, it's time to examine the supporting elements that complete the burger experience: bacon, cheese, toppings, and condiments. These items may seem simple, but each is chosen and prepared with deliberate intent and, in most cases, centralized at an industrial level before being delivered to restaurants. Starting with bacon, Five Guys sources thick-cut, naturally smoked strips from approved pork processors in the US. The bacon is not fully cooked at the factory. Instead, it's partially cooked or pre-rendered to about 60 to 70% doneness, then chilled and vacuum packed in clear plastic pouches. These pouches are labeled and sorted by weight and count per case, with each case tagged for traceability. The bacon is cooked to completion in the restaurant, where staff lay it flat on the grill and crisp it to order. This two-step process, initial industrial cooking followed by final preparation, ensures food safety, flavor development, and grease reduction. The manufacturing process for Ruffles potato chips begins long before a potato even enters the production facility. It starts with agricultural planning and controlled sourcing. Ruffles, as a brand under Frito-Lay, utilizes proprietary potato varieties that are cultivated specifically for chip production. These aren't the same types of potatoes used for baking or mashing. Instead, Frito-Lay contracts with dozens of partner farms across the United States and other regions to grow chipping potatoes, varieties like Atlantic, Snowden, or proprietary Frito-Lay hybrids that are selected for their specific characteristics: high dry matter content, low sugar levels, uniform shape, and dense texture. Each crop is grown with tight controls on irrigation, fertilizer use, and harvesting schedules to ensure consistency and minimize storage degradation. Potatoes that are too moist, sugary, or irregular in shape would result in chips that are oily, dark, or fragile, none of which meet the Ruffles brand standard. At harvest, potatoes are collected using automated harvesters equipped with rubber conveyors that minimize bruising. They're loaded into transport trucks and sent to the factory, often within a few days of being pulled from the ground. When the potatoes arrive at the processing plant, they enter the facility through the raw receiving bay. These are enclosed intake areas where truckloads are weighed, logged, and tested before being accepted for processing. At this point, technicians from the quality assurance team extract random samples from the load to check for size uniformity, sugar content, starch levels, and moisture content. Any batch of potatoes that falls outside the tight specification window may be rejected or diverted to other non-chip product lines. Once cleared, the potatoes are offloaded from the trucks into a large receiving pit, essentially a hopper connected to a series of conveyor belts. From here, the potatoes are moved toward the initial cleaning phase. This begins with the destoning drum. As the potatoes enter this large rotating cylinder, jets of water and the rotating action cause heavier materials, like rocks or clumps of soil, to separate and fall through grated bottoms. Potatoes are lighter and are lifted to the next stage. From the destoning drum, the potatoes enter the pre-wash flume system. A flume is a water-filled channel that moves product gently using the flow of water instead of belts. This minimizes physical damage to the raw potatoes while removing dirt and loose debris. The flume water is treated and recirculated through industrial filters and chemical dosing systems to ensure both sanitation and water conservation. In many modern plants, the water used in these systems is part of a closed-loop recovery system designed to reduce environmental impact. The next stop is the rotary scrubber. This is a long, cylindrical machine fitted with internal brushes that rotate as the potatoes pass through. High-pressure nozzles spray water as the tub rotates, scrubbing away any remaining mud, sand, or biological debris. The inside of the scrubber is lined with abrasive surfaces that help clean the rough skin of the potato without cutting into the flesh. The goal here is to deliver a clean, undamaged potato with its skin still intact, ready for inspection. After scrubbing, the potatoes are lifted out of the washer by a cleated incline conveyor and passed through a visual and automated inspection system. In this phase, both human inspectors and camera-based vision systems work in parallel. The conveyor belt is engineered to spread out potatoes into a single layer, and each tuber moves past a combination of high-resolution cameras and infrared sensors. These systems are trained to detect green spots, bruises, cuts, or signs of rot. Any substandard potatoes are rejected via automated diverter arms or air jets, which remove the faulty items from the belt and send them to waste or compost streams. Human operators stationed along the line also remove visibly defective items that machines might miss, such as those with odd shapes that won't slice well on the crinkle-cut blades. Every removed potato is scanned and logged into the factory's waste tracking system, allowing operators to identify trends and address upstream sourcing problems if too many rejects appear from a single truckload. Now that the potatoes have passed visual inspection, they move on to the peeling station. For Ruffles, peeling is essential. While some gourmet-style chips retain their skins, Ruffles chips require a smooth, peeled surface to produce clean, consistent ridges during slicing. Peeling is achieved using a combination of steam and abrasion in what's known as a steam peeler. The steam peeler is a high-pressure vessel that receives a batch of potatoes, seals the chamber, and subjects the potatoes to pressurized steam, usually around 180-220 psi for 8 to 20 seconds. This superheated environment rapidly loosens the outer skin layer by partially gelatinizing the pectin between the skin and the underlying tissue. Once the steam cycle ends, a sudden pressure drop causes the skin to puff and detach slightly from the flesh. Immediately after this, the potatoes are discharged into an abrasive roller peeler. This is a rotating drum lined with rough surfaces, often embedded with carborundum grit, that gently scrubs the now loosened skins away. Water sprays are used to flush away the skins and clean the exposed potato surface. The amount of skin removed is carefully monitored. Too much abrasion would remove usable flesh and increase waste. Too little would leave patches of skin that affect the slicing process. The peeled potatoes are rinsed again in chilled water to stop any residual thermal activity and prevent enzymatic browning. A small dose of food-safe antioxidant, like sodium metabisulfite or citric acid, may be added to the rinse water to preserve the pale color of the peeled surface and prevent discoloration before slicing. At this stage, the potatoes are fully clean, peeled, and ready for their signature transformation, being cut into the iconic ridged slices that define a Ruffles chip. With the freshly peeled and rinsed potatoes now ready for transformation, The next phase in the Ruffles production process focuses on slicing, the moment where whole tubers are precisely cut into their distinctive ridged form. The ridges are far more than a visual or marketing detail. They play a critical role in the chip's strength, texture, and frying performance. This stage involves advanced slicing technology, careful temperature and starch control, and continuous monitoring to ensure each slice is the exact thickness, shape, and structural consistency required for optimal cooking and crispness. The peeled potatoes are transported to the slicing area via gentle, water-based flumes or soft conveyor belts to minimize impact and prevent bruising. Once they reach the slicing units, the potatoes are fed one by one into high-speed rotary slicers designed specifically for crinkle or corrugated cuts. These industrial slicing machines use a rotating impeller or feed wheel to press each potato firmly against a stationary, razor-sharp cutting head fitted with ridged blades. The blades are precisely machined to form a consistent wave pattern, typically with a wave amplitude of 1.5, 2.5 mm and a thickness of around 1.3, 1.5 mm. Unlike flat chip slicing, where a smooth blade is sufficient, Ruffles require a carefully engineered ridged blade made of hardened stainless steel. These blades are aligned at specific angles to produce even, undistorted waves along the chip's entire surface. The sharpness, speed of rotation, and pressure exerted must be perfectly balanced. Too much force or misalignment can result in chips with uneven ridges or broken tips, which would either fry unevenly or be rejected later during inspection. The sliced potatoes are ejected from the slicing drum at high velocity and collected in a shallow trough or on a belt that immediately begins the next critical step: starch removal and surface moisture control. Every potato contains natural starch, and when sliced, a large amount of that starch is released onto the cut surfaces. If not removed, this surface starch can interfere with the frying process, causing chips to stick together, fry unevenly, or develop burnt spots. It can also result in a greasy or gummy mouthfeel, which is unacceptable for Ruffles' clean, crisp texture. To remove excess starch, the slices pass through a multi-stage rinsing system. In the first phase, they enter a flume filled with cold, recirculated water, where they are gently agitated to dislodge free starch. The water in this flume is constantly filtered and monitored for starch content, with automated control systems adjusting flow rate and replacement intervals to maintain effectiveness. Following the first rinse, the slices often move through a series of cascading rinse curtains, sheets of filtered water that fall like waterfalls over the slices as they travel along a mesh or perforated conveyor belt. This helps remove residual starch without applying any mechanical force that could break the delicate ridges. After rinsing, the slices must be dried to a specific degree, not fully desiccated, but dry enough on the surface to allow the hot oil in the fryer to crisp the exterior without creating steam pockets or excessive foaming. This is achieved using a dewatering shaker and an air drying tunnel. The dewatering shaker is a vibrating belt or tray that shakes the slices gently to remove bulk water. The slices then pass under high-velocity air knives, rows of precisely aligned jets that blast room temperature or slightly warmed air across the chip surface. The air knives are tuned to create a shearing effect that strips away surface moisture while maintaining the shape and integrity of the ridged cuts. At this point, the slices are considered ready for frying, but only if they meet one final set of pre-cook inspection criteria. Before entering the fryer, the slices pass through an optical sorting system. This state-of-the-art inspection station uses a combination of high-resolution cameras, infrared sensors, and sometimes laser scanners to detect defects such as green spots, bruising, overly large slices, or broken pieces. Defective slices are rejected with microbursts of compressed air, which knock them off the main conveyor line and into waste or reprocessing bins. The acceptable slices, meanwhile, are evenly distributed across the width of the fryer in feed conveyor to ensure uniform exposure to hot oil. Frying is where the raw slices become what we recognize as potato chips. And for Ruffles, this step is both art and engineering. The chips are fried in continuous fryers, long stainless steel troughs filled with high-temperature cooking oil. The oil is typically a carefully formulated blend of vegetable oils, often including sunflower, corn, or canola oil, chosen for their high smoke points, neutral flavor, and oxidative stability. The oil is filtered, treated, and replaced on a tightly regulated schedule to maintain quality and avoid flavor degradation. As the slices enter the fryer, they are immediately submerged by a submersion conveyor that ensures they stay evenly beneath the oil's surface throughout the cooking process. The oil is maintained at a precise temperature, usually between 170 degrees Celsius and 190 degrees Celsius. This range is critical. Too cool, and the chips absorb oil and turn soggy. Too hot, and they brown too quickly or develop burnt notes. Each chip is cooked for approximately 2 to 3 minutes, depending on thickness, oil composition, and desired moisture content. Inside the fryer, the chips expand slightly and crisp as their internal water content rapidly evaporates. The ridged surface of Ruffles causes the chip to fry unevenly by design, creating micro variations in texture that result in a more substantial bite and greater structural integrity. The ridges also slow oil drainage, allowing a slightly longer dwell time that contributes to the chip's durability and resistance to breakage during dipping. The fryer is equipped with multiple sensors and flow meters that measure oil temperature, turnover rate, chip feed rate, and even in-oil moisture concentration. These data are analyzed in real time by the factory's central control system, allowing operators to make immediate adjustments. In many facilities, the frying process is linked to upstream slicing sensors. For example, if slightly thicker slices are detected coming from the cutter, the fryer conveyor speed is slowed accordingly to ensure proper cook time. As the chips emerge from the fryer, they pass through an oil draining phase. A vibrating conveyor with a perforated surface allows excess oil to drip off. This is immediately followed by an air cooling system that begins to lower the chip's temperature, halting further cooking and locking in texture. Cooling is essential not only for texture stability, but also to prepare the chips for seasoning, which happens shortly after. But before we get to seasoning, there's a critical interlude in the process: moisture analysis and inline quality control. At this stage, a small percentage of chips are diverted through a sampling chute to a nearby test station. Here, technicians use moisture analyzers, color meters, and even acoustic crispness testers to evaluate product characteristics. These tests ensure that the chips meet the factory's targets for final moisture content, color uniformity, and physical integrity. As the freshly fried and cooled Ruffles chips exit the fryer and pass through preliminary quality control, they enter one of the most dynamic and highly controlled stages in the factory: seasoning. This is the phase where the chips receive their final flavor identity, whether it's the original lightly salted variant, sour cream and onion, cheddar and sour cream, jalapeno ranch, or any of the other regional and seasonal flavor options Ruffles is known for. Applying these flavors evenly, consistently, and at high speed while preserving the chip's structural integrity and minimizing waste is a challenge that modern factories solve using specialized equipment and real-time process monitoring. The chips arrive at the seasoning station on a wide, inclined conveyor or vibratory tray that serves two main functions. It spreads the chips out into a single layer to prevent overlap, and it gently agglomerates chips to control their flow into the seasoning drum without damaging them. Due to the ridged shape and the thicker cut of Ruffles compared to standard potato chips, seasoning application must account for deeper surface area and variable orientation. Some chips will face ridge side up, some down, some angled. Seasoning application takes place inside a rotating tumbler drum, also called a flavor drum or seasoning cylinder. This stainless steel drum is set at a slight incline and constantly turns on its horizontal axis, gently lifting and tumbling the chips while they rotate through it. At the entrance to this drum, a continuous metered flow of seasoning powder is dispensed through an auger-based dosing system. The seasoning blend, pre-mixed according to a proprietary formula, includes a combination of salt, natural and artificial flavorings, cheese powders, dehydrated dairy, onion and garlic powders, spices, yeast extract, and anti-caking agents. The dosage rate of the seasoning is tightly controlled via real-time feedback systems. Optical sensors measure the chip volume entering the drum, and the dosing screw adjusts the delivery rate to maintain an ideal flavor to surface area ratio. Too much seasoning leads to clumping, over-salted chips, and waste. Too little results in bland or unevenly flavored chips that fail quality checks. For cheese-based seasonings, which are more moisture sensitive, the flow system may include a nitrogen-purged hopper or desiccant units to prevent clumping in humid environments. Inside the flavor drum, fine misting nozzles also spray a light coating of oil to help the seasoning adhere evenly to the chip surface. This atomized oil does not soak the chips, but rather creates a microfilm that holds the powder in place without compromising crunch. The rate of oil application, angle of spray, and temperature are all adjusted based on the type of seasoning used. For example, heavily coated varieties like cheddar and sour cream require more binder oil and a slightly longer tumbling duration to ensure every chip is fully and evenly coated. Throughout the seasoning process, line operators and quality assurance technicians take random samples every few minutes. These samples are assessed for seasoning coverage, color intensity, and surface powder levels. In more advanced factories, seasoning uniformity is checked with hyperspectral cameras that scan the chips as they exit the drum, detecting variations invisible to the human eye and triggering alerts or auto-calibration if inconsistencies are detected. Once the chips have been properly seasoned, they are transferred to the packaging phase. This is a highly automated and synchronized system that must meet several objectives simultaneously. Protect the chips from breakage, preserve freshness, prevent contamination, provide product information to the consumer, and maintain traceability for safety audits. Packaging begins with product accumulation. Conveyors from multiple seasoning drums may feed into a single accumulation hopper or weigher, depending on line configuration. This hopper temporarily holds chips before they're dispensed into individual bags via a multi-head combination weigher. A multi-head weigher is an advanced piece of equipment with multiple radial feed hoppers arranged in a circular pattern. Each hopper releases a small portion of chips, and a central computer instantly calculates which combination of hoppers adds up closest to the target weight, say 28.3 grams for a single serve bag. This combination is released simultaneously into a timing hopper, which drops the exact weight into a vertical form-fill-seal packaging machine. The VFFS machine forms bags from a continuous roll of printed plastic film, often made from multi-layer laminate materials with barriers against oxygen, light, and moisture. As the chips drop from the weigher into the forming tube, the film is pulled around the tube, sealed lengthwise, and sealed again at the top and bottom with heated jaws, creating a pillow-style bag. Before the top seal is made, a precise dose of nitrogen gas is injected into the bag, a process known as nitrogen flushing. This replaces the oxygen-rich air inside the package to reduce oxidation, extend shelf life, and protect the chips from crushing by slightly inflating the bag. Once sealed, each bag moves through a print station where batch codes, production time, plant ID, and expiration dates are applied using inkjet or thermal printers. Bags then pass through check weighers to confirm accuracy. Any bag outside the designated weight window is automatically rejected and diverted to a rework bin. Metal detectors or X-ray systems scan every bag to ensure no foreign objects have entered the product during processing. This is standard for all snack food production and a critical part of food safety compliance. From there, the sealed and verified bags are grouped into cartons or display trays by robotic case packers. These cartons are sealed with tape or glue and labeled with barcodes and tracking information. Finally, cartons are stacked onto pallets by robotic palletizers, often using suction cup grippers or clamp arms to gently stack without damaging contents. Pallets are wrapped in stretch film and staged in the finished goods warehouse, which is climate controlled to preserve chip texture and flavor. At every point along this packaging line, sensors, programmable logic controllers, and SCADA systems monitor performance metrics, line speed, reject rates, weigher accuracy, sealing temperature, film feed rate, and more. Maintenance logs and process trends are analyzed weekly to identify emerging issues, improve throughput, and reduce product loss. Beyond the physical movement of chips, there are strict sanitation and allergen management systems in place. Since some Ruffles flavors may contain milk, cheese, or other allergens, production lines must be deep cleaned between flavor runs. Clean in place protocols involve dismantling sections of the line using high-pressure washdowns, food-safe detergents, and microbial swab testing. Detailed records of every cleaning cycle are logged and audited regularly. In addition to cleaning, factories must manage cross-contamination risk during flavor changeovers. This includes running purge batches, segregating flavoring agents in separate storage silos, and using dedicated feed lines wherever possible. Every batch of Ruffles is linked back to a full traceability profile, covering raw material lot codes, equipment used, line operator IDs, and environmental conditions during processing. As the freshly packaged Ruffles chips leave the main production floor, the final phase of manufacturing comes into focus. A sophisticated web of logistics, sustainability efforts, continuous process optimization, and digital innovation. While the chips themselves are complete, the factory does not pause. Instead, a parallel system of data analysis, quality assurance, and supply chain orchestration continues operating in the background, ensuring the product not only meets current demand, but evolves to meet future expectations. These behind-the-scenes processes are integral to the long-term efficiency, environmental responsibility, and market success of Ruffles. At the heart of these operations is a factory-wide data infrastructure that tracks every input and output, from raw potatoes to finished pallets. Each batch of Ruffles produced is logged into an integrated manufacturing execution system. This software records the origin of each ingredient, the time and conditions of each processing step, the performance of every machine along the line, and even environmental metrics like room humidity and oil turnover frequency. The MES integrates with enterprise resource planning systems, providing real-time visibility into inventory levels, sales forecasts, and raw material consumption. This data is not merely archived, it's analyzed continuously using advanced analytics platforms and AI-based algorithms. These systems look for patterns in machine downtime, chip reject rates, oil consumption per batch, or seasonal fluctuations in potato solids. If a fryer begins to show a subtle increase in oil absorption, or if seasoning coverage becomes slightly more variable, the system flags it. Maintenance crews and process engineers receive alerts and can intervene before the issue affects product quality or efficiency. Predictive maintenance models also help avoid equipment failure by identifying when motors, pumps, or slicers are approaching wear thresholds. One of the key areas of focus in modern Ruffles factories is oil management. Frying oil is both a major cost and a major variable in product consistency and sustainability. The oil in the continuous fryer is constantly recirculated through filtration units that remove chip fines and particulates. Inline sensors monitor the free fatty acid content, color, and total polar materials in the oil, 3 indicators of oil degradation. When these metrics exceed defined limits, the system initiates partial or full oil replacement protocols. Some facilities have implemented smart fryer systems that dynamically adjust oil flow and heat profiles based on chip load and moisture level, significantly reducing oil turnover without compromising flavor or texture. Environmental sustainability is another priority embedded into Ruffles manufacturing. Frito-Lay, the parent brand, has committed to reducing water, energy, and greenhouse gas emissions across its snack food plants. One way this is achieved is through water reclamation. The flume water used to transport, wash, and rinse potatoes is filtered, UV treated, and reused multiple times before final disposal. Similarly, the steam peelers are equipped with condensate recovery systems that recycle steam condensate back into the boiler system, conserving energy and reducing water use. Electricity usage is optimized through variable frequency drives on conveyors and pumps, while LED lighting, motion sensors, and insulated cooling tunnels help minimize unnecessary energy waste. Some Ruffles production plants are now partially powered by renewable sources, including solar panels and biogas captured from on-site food waste digesters. Waste heat from fryers is recovered using heat exchangers and used to preheat incoming wash water, further boosting energy efficiency. Waste management is another crucial part of the factory's operations. Trimmings from biscuit cuts, chips rejected for size or overcooking, and seasoning overage are all collected, logged, and sent to animal feed processors or converted into biofuel when food safety protocols allow. Even the excess oil removed during de-oiling phases is collected, filtered, and sold to biodiesel manufacturers. Packaging materials are optimized for minimal plastic use, and packaging engineers continuously evaluate new laminates that offer better barrier performance with reduced environmental impact. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase, designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated, separated into single file, and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking, and an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the Almond Joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor, and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coded, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from Coconut Grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers. And the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package. Historically, gum base was made from natural tree resins like chicle, a latex-like substance harvested from the sapodilla tree, which grows in Central America. However, nearly all modern bubblegum factories now rely on synthetic gum bases. These are specially formulated blends of food-grade elastomers, resins, waxes, plasticizers, and softening agents. The use of synthetics provides far greater control over consistency, shelf life, and bubble blowing capability, which is critical for mass production and distribution. The raw materials used in synthetic gum base are delivered to the factory in large sacks or drums, and each ingredient is sampled and tested before entering the production line. Elastomers such as polyisobutylene and polyvinyl acetate provide the stretchy, elastic properties needed for bubble blowing. Resins act as binders that hold the gum together. Waxes like paraffin and microcrystalline waxes are added to soften the mixture and give the gum its pliable, non-brittle chew. Plasticizers such as glycerol, esters improve texture, while fillers like calcium carbonate or talc give the gum body and density. Each of these materials must be prepared for mixing. Solid components are broken down using industrial grinders and micronizers to achieve a uniform particle size, which ensures even distribution throughout the base. Waxes and resins are often pre-melted in jacketed stainless steel tanks equipped with indirect heating systems to prevent scorching. The raw elastomers are delivered in dense, rubbery blocks that are cut down using industrial dicing equipment before being added to the mix. Accuracy in measuring each component is vital. The slightest deviation in the amount of resin or wax can drastically alter the final chewiness and bubble forming capability of the gum. Now it's time for the blending of the gum base, which happens in large Sigma blade mixers, named for their two interlocking Z-shaped blades that rotate in opposite directions to fold and knead heavy materials. These mixers are specifically designed to handle high viscosity compounds like gum base. The various pre-measured ingredients are added to the mixer in a specific sequence. First, the elastomers are introduced and given time to soften and break down under shear force. As they begin to form a uniform mass, resins are added to bind the structure. Waxes and plasticizers follow, blending smoothly into the mixture to help reduce internal friction and improve processability. This mixing process is not quick. Depending on the size of the batch and the recipe, the blending cycle can last anywhere from 45 minutes to several hours. The mixer itself is equipped with internal thermocouples to continuously monitor the temperature of the mass, which is maintained between 60 degrees Celsius and 90 degrees Celsius. Too low and the materials won't melt and blend. Too high and thermal degradation could occur, affecting the safety and performance of the gum. Operators observe the process through viewing ports and rely on torque readings and viscosity data from the mixer's internal sensors to determine the exact moment the gum base is fully homogenized. Once the gum base has reached the correct consistency, it is discharged from the mixer. This is a challenging step because the base at this point is extremely thick, sticky, and hot. To facilitate removal, the bottom of the mixer opens hydraulically and the heavy base is dropped onto a large stainless steel cooling table or fed directly into a sheeting system. The cooling table is actively temperature controlled using circulating chilled water to begin lowering the temperature of the gum base as quickly and evenly as possible. Large Teflon-coated rollers may be used to flatten the mass slightly, increasing surface area and speeding up the cooling process. The goal at this point is not to bring the base down to room temperature entirely, but to reduce its temperature to a workable range, usually between 40 degrees Celsius and 50 degrees Celsius, so it can move to the next stage without sticking to equipment or losing its plasticity. The partially cooled gum base is then cut into manageable blocks using high lubricity heated cutting blades. These blocks are weighed, labeled with batch numbers, and either sent directly to the next phase of production or stored in temperature-controlled holding rooms for later use. Even in this early stage of production, quality control is already an active part of the process. Samples of gum base are collected from each batch and taken to the plant's in-house laboratory, where technicians test them for elasticity, tensile strength, softness, and melt behavior. Specialized equipment such as rheometers, durometers, and texture analyzers are used to measure mechanical properties under simulated chewing conditions. This ensures that the gum base will respond correctly when blended with sweeteners, flavors, and colors in the next stages of processing. It's also worth noting that not all gum base formulations are the same. For bubblegum specifically, the formulation includes higher levels of elastomers and plasticizers than in chewing gum intended for long-lasting flavor or dental benefits. Bubblegum is designed to be more pliable and capable of trapping air, so it can form large bubbles without breaking too easily. This performance requirement influences everything from ingredient selection to mixer settings and even downstream cooling methods. Therefore, each variation of gum base may require its own unique process settings and equipment parameters. In the next stage, the base will be transferred into another high-capacity mixer, this time designed to handle not only dense material, but also sensitive flavor components and volatile sweeteners. The balance of heat, pressure, timing, and sequencing here is critical. Too much heat can break down sugar molecules and destroy flavor integrity. Too little, and the gum won't mix properly. The entire system must operate like a symphony of mechanical precision and food engineering science to ensure that every piece of bubblegum delivers the iconic chew and flavor burst that consumers expect. With the gum base now fully prepared, cooled, and tested, it's time for one of the most critical stages in bubblegum manufacturing: the integration of sweeteners, softeners, and flavorings. This is where the bland, rubbery core transforms into something enjoyable and familiar. The sweet, fruity, chewy product capable of inflating into perfect pink bubbles. At this point, the gum base is still a nondescript mass, pliable, tacky, but utterly flavorless and unappealing. The magic is about to happen in an industrial mixing process that must blend these next components evenly while preserving the precise texture and chew required for successful bubblegum performance. Before anything is added to the gum base, it must be brought back to a specific working temperature. Though the blocks were cooled after being discharged from the original base mixer, they must now be re-softened for further blending. This is accomplished using a series of jacketed holding vessels or warming conveyors that apply gentle, indirect heat, usually via hot water or steam circulating through double-walled stainless steel pipes. The temperature is carefully raised to a range of 40 degrees Celsius to 60 degrees Celsius, just enough to make the gum base pliable again without overheating or causing degradation of any of the soon-to-be added ingredients. The re-softened gum base is then introduced into a second type of mixer, often a horizontal batch mixer or a planetary mixer specifically engineered to process high-viscosity food materials. These mixers are outfitted with double sigma blades or paddle arms capable of kneading the gum base with immense force. Once the gum base begins to rotate and fold, the sweeteners are added gradually. These include powdered sugar, also known as icing sugar, glucose syrup, and sometimes corn syrup solids. Each of these sweeteners serves multiple purposes. Powdered sugar provides bulk, texture, and long-lasting sweetness. Glucose syrup contributes a softer mouthfeel and prevents crystallization. Corn syrup solids help maintain chewiness and shelf stability. In some formulations, especially those designed for sugar-free bubblegum, bulk sweeteners such as sorbitol, xylitol, or mannitol are used in place of sugar. These polyols require different handling due to their moisture absorption characteristics and sensitivity to heat. In any case, each type of sweetener must be fed into the mixer in stages, allowing the gum base to fully absorb and integrate the new material before more is added. This prevents clumping and ensures that the resulting mixture remains smooth and pliable. Industrial-scale screw feeders or vacuum conveyors may be used to introduce these ingredients directly into the sealed mixing chamber to maintain cleanliness and prevent contamination. Following sweetener addition, softeners such as glycerin and vegetable oils are introduced. These materials are essential to prevent the gum from becoming brittle over time and to give it the desirable, soft, elastic texture that bubblegum is known for. The quantity and timing of softener addition are precisely calculated. Too little and the gum will harden quickly after production. Too much and it will become greasy and sticky, especially under warm storage conditions. Glycerin, in particular, helps trap moisture within the matrix of the gum and acts as a plasticizer, allowing the final product to retain its chew even after prolonged shelf life. Once the bulk of sweeteners and softeners are integrated, it's time for one of the most delicate and carefully timed steps in the entire production line: the addition of flavorings and colors. Flavor compounds used in bubblegum are typically a blend of fruit, esters, vanillin, and long-lasting artificial flavors engineered specifically for gum applications. These flavors must be oil-soluble and thermally stable, as any degradation can result in bitterness, loss of intensity, or altered taste profiles. The most iconic bubblegum flavor is a blend of banana, cherry, cinnamon, clove, and wintergreen, artfully balanced to create that familiar pink taste that people associate with classic bubblegum. These flavoring compounds are often concentrated liquids or emulsified pastes, and they're introduced in the final stages of mixing to preserve their volatile aroma compounds. If added too early, the heat and shear of the mixer could evaporate or chemically alter them. The flavors are poured in slowly while the mixer runs at a reduced speed, allowing gentle incorporation. Some manufacturers use pre-encapsulated flavor beads that dissolve slowly during chewing, extending flavor release over time. Coloring agents are added simultaneously or immediately after. These are usually food-grade dyes, such as Red 3 or Red 40, depending on regional regulations, and are added in liquid form or as pre-dispersed powders. These colorants are not just about visual appeal, they help consumers identify and associate flavor with appearance. For classic bubblegum, the universal hue is a bright bubblegum pink. The dye must be evenly distributed throughout the batch, and to do this effectively, the mixer must achieve total homogeneity without overworking the gum or exposing it to heat that could cause the color to fade or change. During this final blending stage, the entire gum mass is constantly monitored. Operators inspect the mixture for uniformity, gloss, elasticity, and color consistency. Samples may be extracted from the mixer at regular intervals and manually kneaded or stretched to ensure no streaking or spotting. Texture and pliability are tested by compressing and stretching a small piece by hand or using mechanical texture analyzers. If any inconsistency is found, whether it's too stiff, too soft, uneven in color, or lacking in flavor, the batch may be reprocessed or scrapped entirely, depending on the deviation severity. Once the gum reaches the desired final formulation, it's discharged from the mixer onto a temperature-controlled rolling table. At this stage, the gum has taken on its familiar look and feel: soft, elastic, vibrantly colored, and bursting with aroma. However, it's still a massive block of uncut material, far from the small, uniform pieces sold in stores. To prepare it for shaping and portioning, the gum is flattened using motorized rollers that compress it into thick sheets. These rollers are heated just slightly, enough to keep the gum pliable, but not so hot that it becomes sticky or begins to sag. The sheeted gum is then conveyed into a sizing line, where it passes through multiple sets of progressively narrower rollers to reduce the sheet thickness to the exact target for the final product. Whether the gum will be cut into strips, rolled into tape, molded into spheres, or formed into pillow-style pieces depends on the final product format. The sheet thickness must be precise. Too thick, and the gum will be too large to chew comfortably. Too thin, and it will tear or lack substance. Precision slitter blades then slice the gum into long ribbons, which are cooled again on conveyor belts using ambient air or chilled tunnels. These ribbons are stacked and allowed to rest briefly in temperature, dent, and humidity-controlled zones. This rest period, sometimes called the conditioning phase, allows moisture and elasticity to equilibrate across the entire piece of gum. It helps stabilize the internal structure and prepare the gum for cutting, shaping, and packaging without causing cracking or deformation. At this point, bubblegum is fully formed in its raw shape, but still unwrapped and unpackaged. The product is ready for the next phase, which involves high-speed forming machines, wrapping systems, and final packaging lines designed to handle thousands of pieces per minute. These systems require their own precise engineering and synchronization to maintain the integrity and appeal of the final product. Now that the bubblegum has been properly flavored, colored, sheeted, and rested, it enters one of the most mechanically intricate and visually satisfying stages of production: shaping and cutting. At this point, the gum exists in long, flat ribbons of pliable, glossy material, carefully rolled and stacked in conditioned zones to ensure uniformity and stability. These ribbons are conveyed in single file onto a forming line that uses high-speed, synchronized mechanisms to turn raw sheets into the iconic forms consumers recognize, whether small pillow-style pieces, sticks, chunks, tape rolls, gumballs, or extruded logs. Let's first explore the most common format, the pillow-shaped bubblegum piece. This format is familiar from vending machines, Halloween candy mixes, and individual wrappers. To achieve this, the bubblegum ribbon is fed into a forming wheel, where it is gently guided through a series of progressive molds or cavity rollers. These rollers are designed with alternating male and female cavities that press into the gum from both sides, creating the shape of a small rectangular block with softened edges. As the ribbon passes through these molds, the gum is compressed and cut simultaneously by a synchronized die cutter positioned just after the final molding wheel. Cutting must be done with extreme precision, as even a millimeter of deviation could affect packaging alignment and product weight. To account for thermal expansion and gum elasticity, the cutting blades are adjustable in both depth and cycle timing. High-speed optical sensors detect the flow rate of the gum ribbon, feeding data into a digital controller that dynamically calibrates the cutter's speed in real time. The gum, now formed into uniform bite-sized pieces, is ejected onto a short conveyor, ready for wrapping. In the case of bubblegum stick formats, like the flat rectangular pieces found in classic packs, the shaping process is slightly different. Instead of molding with rollers, the gum sheets are trimmed on all four edges to create clean, sharp lines. They are then passed through a rotary cutter equipped with hardened steel blades, slicing the sheet into strips of exact dimensions. These strips are stacked and cut again to create individual sticks. The machines responsible for this operation resemble guillotines, but with servo-controlled precision that allows for continuous, non-stop operation at high speeds. The final sticks are conveyed into wrapping units without any manual handling, preserving hygiene and maintaining throughput. Bubblegum tape, a novelty format often rolled into small plastic canisters, requires its own unique process. The sheeted gum is passed through a winding station where it is gently rolled into a flat coil, not unlike a roll of tape. Tension is carefully controlled here, too much pressure, and the coil will deform or stick to itself. Too little, and it will unravel inside the container. Once coiled, the tape is automatically dropped into a custom-formed plastic shell, usually hinged with a pop-top lid. A blade inside the lid allows consumers to tear off a desired length. These plastic cases are injection molded on-site or sourced in bulk and fed into the filling line by vibratory bowl feeders. For gumballs or spherical bubblegum formats, the production method is even more specialized. Instead of being formed from ribbons, these are made using extrusion and spheronization techniques. Warm gum is extruded through a nozzle into a thick rope, which is then cut into small segments by a rotating knife. These segments are dropped into rotating pans, lined with friction-inducing surfaces that tumble the gum continuously, rounding the pieces into spheres through centrifugal motion. Once the balls reach a near-perfect shape, they are cooled and coated in a separate process, which we'll explore shortly. Regardless of the final shape, all bubblegum formats at this stage are unwrapped and uncoated, meaning they are vulnerable to sticking, moisture absorption, and contamination. Therefore, the next critical phase is the wrapping and packaging process, which combines high-speed automation, material engineering, and branding considerations. Starting with pillow pieces and sticks, the gum is immediately conveyed into primary wrapping machines. These are high-speed horizontal or vertical flow wrappers, capable of wrapping hundreds of pieces per minute. A continuous roll of printed film, typically made of polypropylene or foil-backed paper, is unwound and fed through the machine. As the gum pieces travel along a conveyor, the film wraps around each piece and is sealed using heated crimpers that create a back fin seal and two end seals. For some classic styles, twist wrapping machines are used instead, which pinch both ends of a small rectangular wrapper and twist them tightly around the gum. These machines are equipped with sensors that detect gum position and length, ensuring perfect alignment between the product and its printed branding. If even a single wrapper is misaligned or improperly sealed, that piece is ejected from the line via pneumatic diverters. Wrapped pieces are then collected, counted, and transferred in bulk to secondary packaging machines. Secondary packaging is where individual units are grouped for retail sale. For stick gum, this may involve stacking 5 or 10 wrapped sticks into a flat paperboard sleeve, then shrink wrapping the pack. For pillow gum, machines automatically count the desired number of pieces and drop them into a pre-formed bag, which is then sealed using heat or ultrasonic welders. Packaging films are chosen for durability, oxygen resistance, and visual appeal, and often include tear notches or resealable zippers for convenience. In the case of bubblegum tape, filled plastic canisters are labeled and moved through a shrink sleeve applicator, which places a heat shrink label around the container. This sleeve serves both branding and tamper-evident functions, and is tightened using a controlled burst of steam or radiant heat. Finally, canisters are packed into display boxes or larger cartons using robotic pick-and-place arms. Now we return to gumballs, which undergo a unique finishing step: sugar coating. Unlike other formats, gumballs are coated in a hard, shiny shell that not only protects the gum inside, but also adds flavor, color, and gloss. This process is performed in large stainless steel coating pans that slowly tumble the gumballs while successive layers of syrup and powdered sugar are applied. The syrup typically contains water, glucose, and food coloring, which adheres to the surface of each gumball. Then a layer of sugar or sugar alcohol-based powder is sprinkled over the syrup, sticking to it and gradually building up a thick shell. Each coating layer must be dried before the next is added. Warm air is blown gently into the pans while the gumballs tumble, ensuring even drying without cracking or warping the shell. After multiple layers are built up, sometimes more than a dozen, the gumballs are ready for polishing. This final step involves applying a thin layer of food-grade wax or shellac to the gumballs to create the glossy, reflective finish that's so iconic. The polished gumballs are then cooled, inspected, and fed into bulk bagging or capsule dispensing systems depending on their final use. Throughout the forming, wrapping, and packaging process, real-time quality control continues at every junction. Vision inspection systems verify wrapper alignment, seal integrity, and color consistency. High-speed check weighers ensure that every package contains the correct number of pieces and meets the stated weight. Metal detectors and X-ray systems scan for any foreign particles or processing defects. If a flaw is detected, the package is automatically ejected and flagged for review. And behind all of this automation is a digital infrastructure tracking every batch, from base production through to final packaging. Every piece of bubblegum can be traced back to the exact shift, mixer, raw ingredient lot, and even the machine operator responsible for that run. This traceability system is essential for food safety, quality assurance, and regulatory compliance. Once bubblegum has been fully processed, formed, wrapped, and inspected, it enters the final phase within the factory: storage, quality verification, and preparation for shipment. Although the gum is now finished, it still requires careful handling to ensure that its quality and integrity remain intact all the way through to its final retail destination. The post-production environment is just as controlled as the manufacturing zones. Finished goods are transferred into climate-regulated storage areas, where temperature and humidity are strictly maintained to preserve the texture, flavor, and packaging condition of the gum. Each product pallet is labeled with QR codes or barcodes that carry essential traceability information: product type, batch number, production date, and expiration code. These codes integrate with warehouse management systems that organize inventory by shelf life and destination. The warehouse operates on a strict first in, first out (FIFO) system to make sure the oldest products are shipped first, reducing waste and ensuring consistent freshness in the marketplace. Before any product is released for shipping, quality control teams perform final checks. Samples from each lot are pulled and tested for packaging seal integrity, gum softness, visual consistency, and flavor. Any package that fails inspection is flagged, and the rest of its batch is reviewed. All quality records are logged digitally, tying back to the original gum base formulation and mixing parameters. This robust traceability ensures that, in the rare event of a defect or recall, every package's full production history is instantly accessible. Once cleared, The products are palletized and prepared for outbound delivery. Some are shipped to retail distributors, others to vending machine companies, export terminals, or wholesalers. Trucks used for transport are checked for cleanliness and proper loading temperatures to ensure the gum isn't exposed to heat or humidity during transit. Stretch-wrapped pallets are loaded according to weight and stability guidelines, scanned out of the factory system, and then dispatched. Even after leaving the facility, each batch of bubblegum remains traceable, monitored, and accountable. This level of post-production oversight is essential to maintaining brand reliability and consumer trust. It ensures that the bubblegum purchased in a corner store, supermarket, or theme park tastes exactly as intended: sweet, chewy, stretchy, and perfectly made. From polymer blending and base formulation to flavor integration, shaping, wrapping, and final logistics, the entire bubblegum production process is a seamless combination of food science, mechanical precision, and quality management. It's a surprisingly complex journey for a product designed to be fun and carefree, proof that even the most playful confections are supported by a foundation of serious, sophisticated industrial engineering.